So in this video we will study about the how we can understand how we can calculate the cell potential under non-standard condition, and how the concentration of reactant affect the cell potential. So why we are going to study this is because there are two important points we have to think, that corrosion or rusting is that we cannot expect the standard conditions, right? So you can see that if you left the iron in outside atmosphere, so outside atmosphere temperature changes a lot. In the night time it's very cold and in the daytime it's very hot, so it never remain a standard condition. So corrosion, and as we have seen that corrosion and rusting both work like a galvanic cell, and if we have to calculate the cell potential for that type of corrosion or rusting, we cannot calculate based on the standard condition. So we need to understand how we can calculate under non-standard condition. Another example is this: if we have the battery, and we are using any battery which is slowly discharging, like our cell phone batteries, right? Or any this kind of batteries, AA or cell, these batteries slowly discharge. So what happened once they slowly discharge, basically reactant started consuming whatever the reactant in the batteries are there, like electrolytes. So they start consuming and they produce some product. So in that case, once their reactant consume, they slowly decreases their performance. So and after some time they discharge completely. They do not produce any cell potential. So under that condition, that is called non-standard condition. So cell potential at the non-standard condition can be calculated using, or basically we calculate using Nernst equation, and according to Nernst equation, E equal to E, which is E cell is non-standard condition, is equal to standard condition of cell potential minus RT over NF natural log Q. And this is very important equation. You have to memorize this one, where Q is the reaction coefficient, F is the Faraday constant, small n is number of the electrons transfer in the reaction, and F is a Faraday constant. And how we are going to calculate the net Q? So Q we can calculate just like we calculate equilibrium constant. So product divided by reactant, and product concentration divided by reactant concentration. So this is very simple equation, and now we will see how we can derive this equation from this thermodynamic value, which is very easy to understand as well. So let me explain here that as we have studied about that the relationship between free energy and cell potential is equal to minus NF E, and under non-standard condition gives free energy is equal to standard condition of free energy plus RT natural log Q. And if we replace this delta G value into this equation, second equation, then we can write minus NF E equal to minus NF E, which is cell potential under standard condition, plus RT natural log Q. And then if we divide the whole equation by negative NF, then we can cancel out NF, and then we will end up this equation, which is we have just seen in Nernst equation, which is a non-standard condition equal to standard condition of cell minus RT over NF and natural log Q. So if we consider, if we have to rewrite this equation under 25 degree Celsius or at 298 degree Kelvin, so we can place the value of R, T and F, and once we will replace these values, and once we will change this natural log Q to base 10 Q, we will end up this equation, that E equal to E cell in the standard condition minus 0.0952 divided by N and log base 10 Q. So this is another form of the Nernst equation which you need to memorize this one. And then we will study one more important thing here, that if as we have seen that the reaction will keep discharging from here. So Nernst equation and observation. So as the cell start discharge, the current flows from anode to cathode, the concentration will change, the concentration of the reactant will change, and then E cell will also change, right. So what happen when it is start discharging? Basically the cell is spontaneously discharged until it reaches to equilibrium, and once it will reaches to equilibrium, it means E cell is 0 and battery will be dead. So this we can understand in one more way with this slide, that for an example, if we have a galvanic cell where we have pure reactant and they are going to be in the pure product by spontaneous reaction, and if you see that in spontaneous reactions or any spontaneous forward reaction, basically Q is less than K, or we can say delta G will be negative and E cell will be positive. And as we will reach to the equilibrium state, what will happen here? In the equilibrium state, Q will become K and delta G becomes 0, we have seen in thermodynamics. And then at these conditions in equilibrium, basically cell potential will also be 0. It means the reaction will become non-spontaneous, and where the forward reaction and reaction forward and reverse reaction, basically both will be in the equilibrium, and this condition is called the dead battery, or battery is no more. And on the other hand, if we are forced to non-spontaneous reaction, basically this is like a charging of the battery. So in that condition, Q will start be more than K, and then delta G will be positive, and then delta E will be less than 0. So here as we have seen in the Nernst equation, which is a non-standard condition equal to E0 minus 0.0592 divided by N natural log Q. And then another, if we talk about at equilibrium, basically in the equilibrium cell potential will become 0. So we can place E equal to 0, and then we can recalculate how we can calculate the K value, and what will be the relationship between the potential in the standard condition and equilibrium constant. So this is another form of derivation, but here what we need to understand that in the equilibrium, if our reaction reaches at the equilibrium, it means our battery is dead, and under condition of the dead battery, basically Q will be equal to K and delta G will be equal to 0, and E cell will also be 0. So this is important here. In the next video, we will solve some questions related to the Nernst equation so that we can understand better.